continuous probability distributions. Previously, what we've been discussing is probability distributions involving discrete variables. And a discrete variable is a variable that can take on certain values within a given range. So between 2 points in a set, it's possible that there are no values in between two values. It's separate. So it goes from one to the next. Continuous variables, however, a variable that can take on an infinite number of possible given values in a given range. So if you have 2 points that belong to the set, any two numbers, A and B, there's an infinite number of values between points A and B. It's continuous. Some examples may include things like height and weight. You don't go from 200 to 201 pounds instantly. That is a gradual increase with every possible weight in between those two values along the way. Now, probability density. For continuous data, the probability of an event is the area underneath the curve for a desired interval. The total area under the curve is equal to 1. So let's take a look at some of these distributions of continuous data. So this curve is the probability density function, but the area underneath that curve is going to help us solve for the probability of specific events. Now, we'll typically be using versions of this formula which have been simplified using integral calculus to find the area underneath the curve, to find an interval versus a specific value like we did with discrete data. But let's first of all talk about these different types of distributions. First of all is unimodal distributions, meaning there's one peak, and if you notice there's one point where most of the probability is gathered underneath for each of these distributions. And to describe the way that unimodal distribution can be shaped, there's negatively skewed, meaning focus on where the tail is. If it's to the left, the tail, then it's negatively skewed. Here this is symmetrical. It's called normally distributed, which we'll be spending a lot of time talking about this because it's a very common case where values are symmetrically dispersed around the mean. Next, positively skewed means that the right tail, the data, it has a right tail and is clustered around the left-hand side. So if you keep your focus on where the tail of the data is, that will help you in identifying the different types of distributions. Bimodal distribution has two peaks. So here you see there's a peak here, peak there. This distribution may occur when a population consists of two groups with different attributes. For example, the distribution of adult shoe sizes is bimodal because men tend to have larger feet than women do. So if your sample included both men and women, there would be a mean for the women's average size of their feet and men. Not to say that there couldn't be a man with a small foot or a woman with a large foot, but the average for each of those subgroups is different, and therefore the data will cluster around each of those averages. Now, for this right here, these bars look like discrete data with whole values, but the distribution's titles are still valid. So, describe the spread of data in each of the following distributions. This is symmetrical because it's balanced left and right, and it's unimodal, meaning that there's one peak. This right here is skewed right because the tail is on the right-hand side. This is non-symmetric bimodal. So there's two means, but it's not, and that means that it's bimodal, but it's non-symmetric because this one is clearly larger than this one. This is called a uniform distribution, meaning that the probability of each outcome is equally likely. Skewed left, the tail is on the left-hand side. Symmetric bimodal, both are equal sizes, symmetric, and bimodal meaning that there are two peaks or two averages. So we're going to start off with our first continuous data probability distribution, which is the uniform distribution. So we've seen something similar to this when it comes to uniform probability with discrete data. But for a continuous variable, there are some slight changes. If each outcome in a continuous interval with endpoints A and B is equally likely, then the random variable has a uniform distribution. So notice that this right here, the probability mass function up top, this is just the upper line, the function that describes the probability with all of the area underneath. This is a straight line because each outcome is equally likely. And what we're doing is looking at the likelihood of some event between A and B, a continuous variable, and the likelihood, the only possible outcomes happen between A and B inclusive. So if we're looking for the probability that x is less than a particular value of x, notice this is capitalized, referring to the random variable, lowercase x referring to a specific value of that random variable. It's going to be finding the area underneath the curve, the formula for the area of a rectangle, length times width. So keep that in mind. This is always coming from something. Try your best to understand it, not to memorize it, because these all look similar. Probability that it's less than a particular value. Well, if the values are between A and B, and our interest is whenever it is less than or equal to x, that means that the value of x must be between A and x. So the side of the rectangle here is x minus A, explaining this component. Now, in order for this right here to have the area equal to 1, notice that B minus A is the length of this side of this giant rectangle, which has all of the probability underneath it. And if the length times width, we have B minus A in the numerator, then this side would have to be equal to B minus A in order for that area to be equal to 1 underneath the curve. So that means we're going to multiply, in order to find this rectangle in red, this length on the rectangle is 1 over B minus A. And when we multiply those together, then we get our result. So that being said, the area of a rectangle formula is how we derive each of these different versions of the same formula. Let's use an example here. The first commercial break to happen in the first quarter of a football game happens anytime between 10 and 20 minutes. What is the probability that a commercial takes place within the first 14 minutes? So this is the probability that x is less than or equal to a specific value, and we'll just try to keep both of these in the window here. Less than a particular value. So here, this is our value is 14, and A is 10 because that's the lowest possible value we could have for our time. It could be at exactly 10 minutes. So substituting into our formula, that is 14 minus 10 for this side here, and the vertical component is 20 minus 10, which is 1 over 10 for the height, and we get our probability. So that being said, we're going to move forward to a different type of probability called the exponential distribution. Now, in the textbook, this is the waiting time. We previously covered for discrete variable waiting time with with geometric distributions. It's q to the x times p, where that's the number of failures until a success occurs. But this is different as in talking about the actual time, length of time. If the random variable being measured is the waiting time, then the exponential probability density function can be used to approximate probabilities. So the waiting time, if all that we know is the average waiting time for some event, it's going to have this exponential curve for a distribution. And this is the only defining feature that we need for our probability curve. So that being said, mu is the average waiting time. And then this variable k, which is accomplished by 1 over mu, is just a way of simplifying the formula, is the number of events per unit time. E is a constant. It's approximately equal to 2.718. And that is what we'll have as our base for our formula. Now, this is the parent definition of this formula. The probability x is greater than or equal to x. So it measures the area to the right of some value x underneath this curve. So that'll tell us the probability of a specific time or longer. So the alternative to that, if the total area underneath the curve is equal to 1, then if we wanted to get the probability that x is less than a particular value, all we would need to do is 1, the total area, minus the probability that x is greater than a particular value. So this is kind of like the indirect method to solve for this probability that x is less than a particular value. Notice that this component is the same as this. So we're just taking away this component, being left with the remainder. So let's look at a problem. The average waiting time for a call center is 2 minutes. What is the probability that a call is less than 3 minutes? Should say that the waiting time for a call is, but anyways, the given information, mu is 2, so k is 1 over 2, and x is equal to 3. We're interested in when is the probability that x is less than or equal to 3. So in this case, we have 1 minus e to the negative 0.5 to the power, times 3. And when we evaluate this, we get approximately 78%. Now, we use this formula here because we said less than, and we have to remember that our parent definition for our function is for greater than, so we'll use this whenever it's less than to get the left-hand side. So what is the probability that the phone call will exceed 5 minutes? If mu is 2, k is 1 over 2, same details with the exception of exceeding 5 minutes. So our parent definition is already measuring area to the right of a point x, so we just use the e to the negative kx formula and substitute. But I would like to just draw attention to this last example. What is the probability that the call is between 1 and 3 minutes? Now this is an interval. So let's take a look at what that would look like with an illustration. If I had 2 points, x1 and x2, what I could do is take the full area of x1 and subtract the area from x2, the right endpoint. And then that, by taking away this right-hand side, I would be left with the area underneath the curve for an interval. And that's what's been accomplished here. We're going to do the left point minus the right point, and that gap, or that interval, will be the remaining area. So try these questions here, and if you have any questions, feel free to ask.